right, everyone, welcome to the Fastpapers IGCSE mock examination, where today we're going to go over the paper 6, the alternative to practical. So the alternative to practical paper is total 40 marks, and I feel like this paper wasn't too difficult. So we're going to go through it, and hopefully by the end of it, if you had any questions while doing the paper, or you thought, I wonder why this is the answer, hopefully that'll be solved. So let's take a look at what we have. So the first question we're going to start with, a student prepares some crystals of pure potassium sulfate by reacting aqueous potassium carbonate with dilute sulfuric acid. The equation for the reaction is shown. So it's K2CO3 plus H2SO4 gives you K2SO4 plus H2O plus carbon dioxide. So the student places 25 cm cube of aqueous potassium carbonate in a conical flask. Adds a few drops of a suitable indicator to the conical flask. Use the burette to add dilute sulfuric acid to the conical flask until the endpoint is reached and the indicator changes color. Table 1.1 shows the burette readings the student obtains. So remember, a burette can only show up to one decimal place. So all your answers have to be within one decimal place. So for example, you're not going to get an answer of 24.25. So that's not possible. So it'll either be 24.2 or 24.3. Just thought I'd mention that before we go any further. So the final burette reading in centimeter cube was 18.8. The initial reading was 4.2, volume of dilute sulfuric acid. So we need to figure that out. Complete table 1.1 by calculating the volume of dilute sulfuric acid added to the conical flask. So this is very simple. You take your final and you're going to subtract that from your initial minus initial. So if we do that, you're going to have 18.8 minus 4.2. So if you do the math, that's going to give you 6. That'll be a 4 and 14.6. So you're going to put 14.6 here. And remember, they've already given you cm cube over here. So there's going to be no cm cube over here. So make sure you don't make that mistake. If the table gives you the unit, then you don't need to include it in your final answer. So now they're saying, state which solution, aqueous potassium carbonate or dilute sulfuric acid, is the least concentrated. Give a reason for your answer. So let's compare the volumes that we have. So we have potassium carbonate, we have 25 cm cube, 25.0 cm cube. And for sulfuric acid, we figured out that it's going to be 14.6 cm cube. So here's the thing. The molar ratio of potassium carbonate to sulfuric acid is basically the same. So you don't see this 1 mole of potassium carbonate reacts with 1 mole of sulfuric acid, giving you 1 mole of everything. So everything is 1:1:1:1. So there's no sort of other factor into consideration over here. So if we take a look at the volume, so if you want to get the same moles, so let's take, for example, moles is equal to X, for example. So they both have the same number of moles. So if we're going to calculate, so 25 by 1000 into concentration is equal to 14.6 by 1000 into concentration, because they have the same number of moles. So the moles of potassium carbonate is equal to the mole of sulfuric acid because their molar ratio is the same. So because potassium carbonate has a higher volume and sulfuric acid has a lower volume, so for them to be equal, the concentration of sulfuric acid must be greater than the concentration of potassium carbonate. So the way this works is because you need a larger volume of potassium carbonate, it shows that it's less concentrated than your sulfuric acid. So the least concentrated solution, now it's important that you read the question here. So a lot of people might think that, oh, so they're talking about concentration. and we're going to give sulfuric acid. So it's asked for the least concentrated solution. So because we know what the least concentrated solution is, we're going to write down. So you can either write K2CO3, or you can write potassium carbonate. And as for the reasoning, as we've explained before, it's nothing too difficult, nothing too complicated. You're just going to write that a larger volume was used. Larger volume of K2CO3 was used. And that's it. Very simple, 1 mark, no need to complicate anything. So name a piece of apparatus suitable for measuring the 25 cm cube of aqueous potassium carbonate. So you can put either one of a pipette. If you want to be very accurate, then this is probably the way you want to go. But you won't lose marks if you write burette, because both are technically correct and they don't mention accuracy anywhere. So both of these are correct. Name a suitable indicator and give the color change of this indicator at the endpoint. So the endpoint we have to remember is sort of when the pH is neutral. So a lot of us, we might get excited, and when we're writing something like methyl orange, we might write yellow to red. So while that might be correct, so take for example, I'm going to use different colors for this. So methyl orange, when you're at an alkali, it's going to show as yellow. So alkali, it shows yellow. I'll write yellow here. When it's neutral, that's when it shows orange. So neutral. And when it's acidic, you're going to find it's going to show red. So in this case, we're trying to find the endpoint, which is the neutral point. If you go to the acidic point and you write red, you're not technically wrong, but it does mean that you've overshot your solution, which is why we want to stick to what the color scheme is at the neutral point. So you can write a bunch of different indicators as long as you get their end color right. So you can write methyl orange. You can also write phenolphthalein. So an interesting thing about Cambridge is as long as you're phonetically correct, which means that as long as the way you're spelling it sounds the same as the word, then you're going to get marks for that. So phenolphthalein is going to have an H. Phenolphthalein, or you can even put, for example, thymolphthalein. Thymolphthalein. So phenolphthalein is going to be pink to white. So for absence of pink, I'm just going to use this. So pink to white. And thymolphthalein is going to be blue to colorless. Oh, sorry. It's not going to be white. It's going to be colorless. My bad. It's going to be colorless. That's a pretty big error over there, but it's fine. We all make errors sometimes. So pink to colorless. And thymolphthalein is going to be blue to colorless. But because I wrote methyl orange first, I'm going to write that over there. So I'm going to pull that here and say it's going to be yellow to orange. All right, so our next one is going to be, as the student added the dilute sulfuric acid to the aqueous potassium carbonate, they looked for a color change. State what the student should do as they add the dilute sulfuric acid to the aqueous potassium carbonate in the conical flask. So once you guys get to A levels, you're going to do experiments in the lab yourself. Everyone has to do a lab practical. And the thing you're told to do whenever you're doing titration is to always swirl the flask. So this ensures an even mixing of the acid and the alkali and to make sure that the reaction is happening at a proper rate. So describe what the student should now do to obtain crystals of pure potassium sulfate. So here's the thing. The experiment that the student has done so far has been done with an indicator and to find out what the exact value was. So the previous experiment was done to get exact volume of H2SO4. Plus you have indicator solution mixed in. Solution mixed. So if you want pure potassium sulfate, you have to get rid of the indicator. And since you know the exact volume of H2SO4, you can just redo the experiment without the indicator. So the way this is going to go is you're going to write, first of all, mix 25 cm cube of potassium carbonate K2CO3 with 14.6 cm cube of H2SO4 without an indicator. Then you're going to mention that as potassium sulfate is soluble, we're going to have to heat the solution to the crystallization point. Crystallization point, which basically means to remove water. Remove the water, because after all, this is soluble. So you need to get rid of the water to get to your actual crystals of potassium sulfate. So once you're done with that, you're going to cool the solution. So crystals form. Crystals form. And that's it. That's 9 marks, very easy, nothing too difficult. So let's move on to the next question. All right, so there's a lot of steps in this question. You guys can take a break if you can pause the video now if you want to read through it. I'm just going to highlight some key information. Rinse a burette with distilled water and then with solution C. So this is going to be important later on. Run some of the solution, you don't need to know that. Record the initial burette reading. Use a measuring cylinder to pour 25 cm cube of solution B. So what we know is solution B is known. Solution B volume is known. Let's write that down. Add 5 drops of methyl orange and 5 drops of thymolphthalene. So we're going to have a first endpoint, which is again red to orange. So as we've discussed previously, red is acidic, orange is neutral. And when we go to orange to yellow, that's alkaline. And they repeat the experiment with a thymolphthalene indicator. So let's continue with that. So use the burette reading diagrams in figure 2.1 and figure 2.22 to record the readings for experiment 1 and experiment 2 in table 2.1. So let's take a look at what the reading is for experiment 1. So for counting from here, this is going to be 1, 2, 3, 4, and this large bit is going to be 5. So this means that this is 6. So that means if we're counting from 1 and we're going down, this is going to be 1.6. Same thing over here, 21. This is going to be 22. So this is at 21.2. And this one, it's exactly on the large one between 41. So this is going to be 41. And this is important because you can go up to one decimal place. It'll be 41.0. Experiment 2 is going to be the same thing, where we're going to take a look at that. So as it's just below the long line for 5, so this is going to be 1, 2, 3. So this will be 0.4. This one, we're going to go 1, so that's 2, so this will be 10.2. And for this one, this is also 1, so that'll be 20.1. So we're going to fill that in. Very simple. Nothing too complicated at all. 21.2, 41.0, 1. Okay, so let me put that like this. 1.6. For experiment 2, it's going to be the same thing. We're going to have 10.2. We're going to have 20.1. And we're going to have 0.4. So we need to figure out volume added from burette to reach the first endpoint. So let's label these all. So let's call this A, let's call this B, and let's call this C. So volume added from the burette to reach your first endpoint. So it means that how much volume did you add to get to the first endpoint? So your first endpoint is A. So you need to figure out how much volume did you add from 1.6 to get to point A. So this will be A minus C. So this will be 21.1 minus 1.6, which will give you a value of 19.6. Again, no need to add centimeter cube because these are already mentioned over here. Same thing for here. This will be A minus C. So 10.2 minus 0.4 is going to give you 9.8. Now they're asking for the total volume added from the burette to reach the second endpoint. So this is important. That's why they highlighted this, so you don't miss it. They're asking for the total. So you're going to take your reading at B and you're going to subtract the initial reading from that. So for this one, it'll be 41.0 minus 1.6, which will give you 39.4. And for this one, you're going to subtract 0.4 from 20.1 to give you 19.7. It's an interesting two figures over here, but we'll get to that later. Explain why the conical flask is rinsed with distilled water at the start of experiment 2. So this is very simple. Whenever you wash out anything with water, it is to clean the flask. So yeah, to clean the flask. All right, so now we move on to the critical portion of this question. At the start of experiment 1, the burette is rinsed with distilled water and then with solution C. Explain how the volume added from the burette to reach the first endpoint would be different if the burette was not rinsed with solution C. So let's take a burette, for example. So it looks something like this. And then like this, right? So let's say when you're rinsing it out with water. So one of the key properties of water is that it's very good at sticking to surfaces. It has a lot of adhesion. So even after you rinse something with water, there's going to be water left over in the burette. Now, it might be a minuscule amount. It might even be 0.1 to 0.2 ml. But the thing is, when you're dealing with quantities as low as you are over here, so you're dealing with quantities that are 10.2, 20.1. So this 0.1 and 0.2 ml of H2O or water will affect the concentration. So because you're affecting the concentration, you're altering your results. And how are you affecting your concentration? You're lowering the concentration. So the amount of water that you're adding that's stuck to the burette, no matter how minuscule it is it's going to have an effect on the concentration. And as a result, you're going to need a larger volume of the, one second, let me just check real quick. I'm really sorry about that. You're going to need a larger volume of solution C. So it's going to be larger volume of solution C needed. And then you're going to mention over here that the solution would be less concentrated, due to excess water. Due to excess H2. All right, next question. Explain why the conical flask is placed on a white tile during the titration. So this is very simple. If you place it on a white tile, it's easier to see color better. So you're just going to mention very cleanly, very simply, to better observe the color change. Observe the color change. So compare the concentration of solution C used in experiment 1 with the concentration of solution D used in experiment 2. Explain your answer, and it's for 3 marks. So we're going to need to give 3 marking points for this. So let's take a look. If you take a look at these numbers, 19.7, if you multiply this by 2, so you're going to get 14 over here, the decimal here, 9 twos are 18, 18 plus 1 carries, that's going to be 9, and then 1 twos are 2, so that's going to be 39.4, which is coincidentally the amount of solution C you had to add in experiment 1. So solution D required half the amount. So because solution D needed less amount, if we go back to the first question that we did in this paper, where we tried to figure out which one was more concentrated, we found out that the less volume that you use, the more concentrated a solution is. So we're going to go back to this question and we're going to answer it very simply that solution D is more concentrated. Solution D is more concentrated, so you're going to get 1 mark for writing this. Is more concentrated. Then you're going to mention that less volume of solution D was needed. And the 3rd mark is going to be for mentioning that half, you can mention the concentration. So this will be that the concentration of solution D is twice the concentration of solution C. Concentration is 2 times solution C's concentration. Concentration. There you go, 3 very easy marks. So deduce the volume of solution C required to reach the first endpoint if experiment 1 is repeated using 50 cm cube of solution B instead. So for 25 cm cube, we're going to do the unitary method. You needed 19.6. So for 1 cm cube, you're going to need 19.6 divided by 25. So for 50, it's going to be 19.6 divided by 25 times 50. So if you do the unitary method, you're going to get 19.6 into 2. and you're going to end up with 39.2. And remember, there's no unit here, so you need to add a unit. So your 1 mark is for writing 39.2, and your next mark is for writing cm cubed. Very simple. This is a very interesting question that when I first saw, I was a bit startled as well. Say by using 50 cm cube of solution B would cause a problem when finding the volume of solution C needed to reach the second endpoint. So remember, you have doubled your volume from 25 to 50. So when doing that, you've doubled your volume from 19.6 to 39.2. So if you look at the second endpoint in experiment 1, that is 39.4. So if you double 39.4, you're going to get 78.8 cm cube, which is more than the amount that a burette can hold, which is 50 cm cube. So this is going to be greater than 50 centimeter cube. So as a result, the problem that you would face is that the burette cannot hold that much solution C, cannot hold that much solution C. It's a very innovative question. When I first saw it, I was a bit confused as well, but then I gave it a second. I saw that it said second endpoint. And because everything is doubling, if you needed 39.4 at just 25 cm cube, then you're going to need double that amount, which is more than the burette can handle. Another interesting question. Student repeats experiment 2. The student warms solution B in the conical flask before carrying out the titration. State the effect, if any, on the volume, so this is important, on the volume of solution D. So a lot of students, what they're going to do when they see this question is, oh, they warmed it. So that means that this is going to have increased the rate of reaction. But here's the thing, you're increasing the rate of reaction with temperature. So rate increases, which basically means the result is obtained faster. But it doesn't change anything, any moles, it doesn't change. So there's no change in moles or concentration, which is the actual thing you need to change if you want to get more of, let's say, for example, they say any effect on the volume of solution D. Because solution B is not experiencing any changes in moles or concentration. No change. Actually, let me just draw the arrow over here. So no change in moles or concentration. So the effect on volume of solution B is going to be no change, and you're going to write moles or concentration unchanged. Very interesting question. All right, state one change to the apparatus that will improve the accuracy of the results. So because you're using 25 cm cube, you can immediately write a pipette, which is one of the more accurate tools you have. More accurate tools. So over here, just write use a pipette. And there we go. 18 marks, very easy. A bit tricky, but overall nothing too difficult, I would say. All right, so for this question, make sure to consult your sheet over here. So test for anions, as you can see, I've already been taking a look at it. So test for anions over here, you're going to keep this open while you're solving. So solution A is aqueous iron 3 nitrate. So iron 3 nitrate. You're going to go over here for cations. You're going to take a look at iron 3. And let's see what they added first. First portion of solution A adds aqueous ammonia dropwise and then in excess. So you're going to take a look over here. Effect of aqueous ammonia, it forms a red-brown precipitate which is insoluble in excess. So remember that you're writing down your observations. So you're not going to write insoluble in excess. What you're going to write over here is red-brown precipitate formed. Precipitate formed. Precipitate. And for observations, you're going to write no change because it doesn't dissolve, right? So because it doesn't dissolve, there's no change observed. It's very interesting when you think about it that way. To the second portion of solution A is still iron 3 nitrate, which, by the way, is FeNO3. Adds aqueous sodium hydroxide. So what are you going to notice when you do that? If you add sodium hydroxide, if you take a look at the test, again, you're going to get a red-brown precipitate. Again, very easy. Just consult the sheet and you'll be good to go. Red-brown PPT. To the product from B1, the student adds a small piece of aluminum foil. The student gently warms the mixture formed and tests any gas produced. So when you add sodium hydroxide to sodium nitrate, you're going to get, so the product of this reaction is going to be sodium nitrate. So whenever you have a nitrate, if you take a look over here, whenever you add aqueous sodium hydroxide and aluminum foil, you're going to get ammonia. So I'm going to bracket this. So remember, you're observing something. Gently warms the mixture formed and tests any gas produced. So in your test, you're obviously going to have a red litmus paper. So you're going to mention that gas produced, gas turns damp red litmus paper blue. Again, taken verbatim from here, that ammonia is produced, and ammonia is, if you go down over here, you even get the test for that. Turns damp red litmus paper blue. So you don't have to worry about it. It's all mentioned in the exam. Just make sure that you read this question properly and that you're getting the information that you need. So again, we know that this will be ammonia. So the third portion of solution A, the student adds about 1 cm³ of dilute nitric acid followed by a few drops of aqueous barium nitrate. So if you take a look at that, that is the test for sulfate. Acidify with dilute nitric acid, then add aqueous barium nitrate. You're supposed to get a white PPT, but because there's no sulfate in our solution A is iron 3 nitrate. So you're going to write that no change. Again, very simple, nothing too complicated. And for this, as long as you consult the chart, so light green flame color, if you go down here, it's mentioned that a light green flame color is barium. So you're going to write over here barium. And for that, dilute hydrochloric acid. So let's take a look at our, well, they also mentioned here that, and a colorless solution forms, lime water turns milky. So anytime you see lime water turns milky, over here, you know that carbon dioxide gas is produced. And carbon dioxide gas is produced from carbonate ions. So it's going to be barium, carbonate, and this will be carbon dioxide, CO2. Very, very easy, 9 marks. And for the last question, magnesium sulfate is a salt. Magnesium sulfate is soluble in water. The solubility of a salt is the mass of the salt in grams that dissolves in 100 cm³ of water at a specified temperature. Plan an investigation to determine the solubility of magnesium sulfate in water at 50 degrees Celsius. Your plan must include how the solubility of magnesium sulfate in grams per 100 cm³ of water can be found. You are provided with solid magnesium sulfate, distilled water, and common laboratory apparatus. So we're going to start simple. We're going to say measure 100 cm³ of water using a measuring cylinder. So whenever you're doing these types of questions, there's a thing that we call flag posting, where if something feels obvious, you should still write it. Because even if it seems obvious to us, you still have to mention it, because you're writing down an investigation. So an investigation covers all the steps that's taking place. So measuring out water, let's say heating something, using a thermometer, these are all important things that you think might be obvious, but if you write it down in the exam, chances are that you're going to be graded just for writing that. So measure 100 cm³ of water using a measuring cylinder. And then heat the 100 cm³ of water of H2O to 50 degrees, not 250 degrees, but to 50 degrees Celsius, so now you can use whatever heat source you want. I'm going to mention using an electric heater. So already, these seem obvious, but you have to flag post for these questions. Using electric heater and maintain the temperature. Maintain the temperature. So over here, you can mention measured using a thermometer, measured with a thermometer. So all these obvious things that might seem obvious to you, as long as you flag post them, you'll be fine in the exam. Then you say add, either you can write excess MgSO4, magnesium sulfate, or add magnesium sulfate until no more dissolves. And then once you've written that, you're going to say filter to remove undissolved MgSO4. So what you've essentially done this entire experiment is you have a beaker. The beaker is filled with 100 cm³ of water, the amount which you know. So this is your water. And you're going to add magnesium sulfate, MgSO4, and you're going to keep adding until you start seeing magnesium sulfate forming at the bottom. So the way this can go is, let's say you've measured beforehand. So let's say you add 50 grams immediately. Or what you could do is add 10 grams bit by bit. So this is adding in excess because you're adding 50 grams, and this is adding until no more dissolves. no more dissolves. So why is this helpful? Because you want to see how much the water will continue to dissolve magnesium sulfate. But eventually the water reaches a point where it can't dissolve any more magnesium sulfate, and that is known as the solubility of the water. So once you filter to remove the undissolved magnesium sulfate, you're going to be left with residue. So you're going to dry the residue and then weigh weigh it, subtract residue weight from mass of MgSO4 added. And there you go. That's a very easy 4-mark question that you guys have just been able to solve. And that's that for the examination. So again, this wasn't too complex. This wasn't too hard. Hopefully you guys were able to do this well. And if you have any questions, please feel free to reach out to the Fastpapers team. They'll be ready to answer any questions you might have. And yeah, best of luck for the examination. I hope you guys ace it. And yeah, thank you for watching and looking forward to seeing you in person real soon. All right, take care.